Okay, are there any questions? Like, what did we say was an Euler circuit yesterday, the last class?
Well, it has to have the same beginning and end point if it's a circuit.
So a circuit is a path that has endpoints that are the same. Start and end is the same. And an Euler circuit is what? E is for?
Easy, right?
E is for easy and?
Edges.
Edges. That's the main thing, is edges. So I have to have all the edges in the graph in my Euler circuit. So how do I tell if a graph has an Euler circuit or not?
All the vertices have an even number of edges from it?
That's right. If all the vertices have even degree or they have an even number of edges touching them, then we have an Euler circuit. So this is another thing, all even degrees. So that starts with the E too. Euler edges even. And this is easy because we use Fleury's algorithm, which just starts adding edges randomly, right? So I could take any graph and make an Euler circuit as long as it has degree 2 everywhere. What about an Euler path? So I have exactly 2 with odd degree, and I can't have any more or any less. Right? And when I do Fleury's algorithm, what kind of nodes do I have to start with? I have to start with the odd ones. So I have to start on an odd vertex. So for Euler circuits, it doesn't matter which vertex you start on, it should work. You just keep adding edges to your path until you have no more left. So let's do an example. Okay, here's one. Just to make it different than the rest of my graphs. I did. I thought I turned it back on. Okay, our power went out, so we had a little break there, but now we're going to get back to finding an Euler circuit in this graph. And I made it on purpose so all of the vertices have even degree. So if you guys want to double check it for me, I think everything has, except for this one. C and A. There we go. No problem. 1, 2, 3, 4, 5, 6. Good. Now we have a graph where all the vertices have even degree, and we can find an Euler circuit. So this is how you can make problems for you to practice. Just make a random one, and then start making an Euler circuit. So when I do this, I just pick a random vertex. I'm going to pick A to start with. I'm going to need to leave myself some room here to write my path. So let's just go from A to B, and we'll just go along until we maybe have, what's the only problem we might run into?
A corner.
We might leave a stranded vertex somewhere. So that's the only thing we have to check for when we're adding edges here. So what we do when we add one is we pretend that actually it's not there anymore. And just make sure we don't leave anything stranded that is still connected. Or leave ourselves stranded is what really the problem is. Okay, so let's just go ahead and add back BA, then go from A to E, and then E to B. I'm just picking random ones here. There's nothing else. So if anybody wants to pick one, they can call one out. We can go from B to C. I have no other choices, so I can leave B by itself there because I delete that vertex as soon as it's not connected anymore. Okay, so I went from B to C. And then from C, I can choose anything. Let's go to D. From D, I have to go back to C. And then from C, let's go over to...
No, E.
We can't go over to A because then we're stranded, right?
Yes.
So it's good to see that that's a choice we can't make at that point. We don't want to go C to A because then we leave this little loop. So we need to go to E,
Back to C.
back to C, and then
to A.
all the way to A. So there's an example of finding an Euler circuit. And it works just the same as an Euler path, except for on an Euler path you have to start on the odd one, and you should end on the other odd one. So Hamilton circuits do what? So this uses all the edges. A Hamilton circuit uses
All the vertices.
all the vertices exactly once, except for the start and end one, which we will list twice. So in this graph, is there a Hamilton circuit? So we listed A a few times, we listed B a few times. So if it was a Hamilton circuit, I would need to list everything exactly once. So can I possibly make a Hamilton circuit for this graph? I see some shaking of heads. Why?
Internal cycle.
Because I have a little internal cycle with the degree 2 vertex, right? Because D has degree 2, so I need to add those two edges in. But that makes a cycle with C. And I can't make any subcycles in a Hamilton circuit. So that was very good. So we'll just do a summary of graph theory, and then I'll do some review of some other topics that we have. So a graph, usually represented by G, is a set of nodes and edges that join them. And we have paths. We need to know what paths are, and cycles. We have Euler circuits, which use all edges in a graph. And all nodes have to have even degree. And if they do, there's always an Euler circuit. And the algorithm to find Euler circuit is called Fleury's algorithm. And that's basically a random add an edge, unless you can't, algorithm. We have Hamilton circuits. So we have Hamilton paths, Euler paths too. And in parentheses, I'm going to put two odds here for a path. Okay, so it's the same, except I have to start and end on the two odds for the Euler path. So we have the Hamilton circuits and paths also, and they use all the vertices each exactly once, except for the start and end. Okay, and this is a slightly harder problem to solve, but I won't give you any that will be too hard to solve on any tests. So you will be able to tell whether there is one. So what's the algorithm to find, like the generic algorithm that works for everything to find Hamilton circuits? The general algorithm that works for all of them is, the only reason why it's a bad one is because it's exponential. It's the one that lists all possible cycles that use all the vertices and then checks to see if they're in the graph. So if you had no other way to find the solution, you could list all possible cycles and check to see if they're in the graph. And this is an NP hard problem because it's exponential. And we know, because we just finished doing counting, that this is a factorial problem, right? All the orderings of n vertices is n factorial orderings. So NP hard does not mean unsolvable, right? For small graphs, it's definitely solvable, because 4 factorial is 24. Checking 24 things is not that bad. And besides, if you only have 4 nodes, you can probably look at it and tell if it has one, right? Also, if you have a graph that's fully connected, you definitely have one, right? If a graph has all the possible edges, it's called a complete graph. You don't need to know that, but just in case you see complete graph, that's what it means, is a graph that has all of the possible edges. Okay, then we have trees. We talked about that. And a tree is a graph with no cycles. So if the number of nodes is n, then the number of edges is n minus 1 in a tree. So we also had, we might need to find minimum spanning trees, right? So a minimum spanning tree is a tree of minimum weight which connects all the nodes of G. So if I start with G and I want a minimum spanning tree, I just need n minus 1 edges that connect the n nodes, and they should be the minimum weight ones. And Kruskal's algorithm will find that, and this just adds the minimum weight edge. And it repeats that until it's added n minus 1 edges. Except you can't add anything to make a cycle, right? Okay, what if you have 2 edges that are the same weight? You can pick a random one. So it doesn't matter. You can just pick whichever one, and you'll still get the same minimum weight. It might be a different tree, so you might have different solutions, but you'll have the same total weight. You just pick a random one if you have 2 edges with the same weight. Okay, we have our matrix representations for graphs. So that was an adjacency matrix. And it was symmetric. And it's a good computer representation for a graph. By the way, how do I write down an edge? Like if I were to list all my nodes, it's easy to list the names of the nodes. But what about the edges? What do I normally do?
The 2 vertices that it joins?
I list the 2 vertices that the edge is connecting. So, and I usually put a comma in between them, so I make an ordered pair. So to represent an edge, I would put A comma B, just like in our binary relations. And if I'm going to list a graph, I would tell whether it's directed or not. So if it's not directed, then AB actually means it goes both ways. AB equals BA, and both of them are in there.